Okay, so welcome to application problems from linear systems of equations. So I have pulled this little animation to show you what it's like to canoe against the water. What does this mean, against the water? Well, look, imagine that you were in a very, very still pond, right? So here is the super still pond. It's not moving, and you are in a boat. Hmm? There's a man in the boat or a woman in the boat. And this person can row this boat, kayak, whatever you want to call it, at say 5 miles per hour. Now, let's imagine that you had a river, and this river is like the Genesee River, is flowing in that direction at say 3 miles per hour. Now, if you were to take a boat and you were to put this boat on this river, nothing at all, no person in it, nothing. The boat also would travel in this direction at 3 miles per hour. But let's take this man or this woman, this person, and put them into this boat and have them row. Now we know this person can go at 5 miles per hour. The river on its own is flowing at 3 miles per hour. So together they would travel in that direction at 5 plus 3 or 8 miles per hour. If they're going in the same direction as you see in this picture, this is called with the current. Now what you see in the YouTube video I have put above is going against the current. What that means is, let me draw a picture again. So here's your river. It's flowing in this direction at 3 miles per hour, and this person here is on the river, but this time this person is going that way. So this person can row in this direction at 5 miles per hour, but the river is pushing him or her in the other direction at 3 miles per hour. So the net speed, the net speed, net speed, meaning the combined speed, right, is 5 minus 3 or 2 miles per hour. You can sort of see that in the video above. Uh, especially if you look at like minutes 50, at like the 50-second mark on that YouTube video, this person's having a really hard time going against the current, despite the fact that they are rowing canoeing pretty strongly. Suddenly they hit this patch with the current and they can barely move. In fact, at one point, the current pushes him back. So you can sort of see the effect of going against the current. And you can again see how the speeds relate. So this speed here is called still water, right? And so with the current, you'd see it's the still water speed, um, still water speed added to the speed of the current, right? So this is still water plus current. This is still water, excuse me, still water minus current when you're going against. Now, these situations are the same whether you're going in water or air. I understand that canoeing may not be a universal experience for everybody, but certainly you have run into the wind when there's wind blowing at you and run with the wind pushing you along, because sort of one's a whole lot easier than the other. All right, now that we sort of have an understanding of this, let's take a look at a problem here. So it says Tim is kayaking on the Genesee River. His average speed is 4 miles per hour when paddling with the current. So when paddling with the current, that's this situation here. and it's 3 miles per hour when he's paddling against the current. Paddling against the current. That's this situation here. Determine the speed of the kayak in still water. Right? So determine the speed of the kayak in still water and the speed of the current. So we have to find two things. So just as before, let's start with what we have to find. So let's say S is equal to the speed of the kayak in still water, right? And let's say C is the speed of the current. So we've got these two S and C. So to draw an analogy with the picture above, S would be 5. So S in this example here would be 5 and C would be 3. So if you're going with the current, then the speed is S plus C, and against the current, the speed is S minus C. Right? That's what we did there, and that's what we did here. All right. So let's see if we can come up with some equations. Now notice that we have two things that we don't know. So two unknowns. This means that we need two equations, just like we have been solving so far, because if you have two equations, we can use either addition method or substitution method to find the two unknowns, right? To solve, we need two equations to solve, right? So let's see if we can come up with two equations. So up here it says the average speed, his average speed is 4.5 miles per hour when paddling with the current. So if he's going with the current, his average speed is S plus C, which is supposed to be 4.5. Against the current, it says his average speed is 3 miles per hour. So against the current is S minus C is 3. Make sure you put the still water first, because otherwise that means he's not going to make progress if you put it afterwards. And hopefully the current is slower than your rowing speed. Now you solve that system. Pretty easy to solve. You can use either the substitution method or the addition method. I'm going to use the addition method because I see that the C's will cancel out if I were to add these. So S plus C and S minus, if I add them, then I get 2S. The C's cancel. I get 7.5. And then I divide by 2. Excuse me. And I get S equals to, calculator, 7.5 divided by 2. I didn't get it wrong there. 7.5 divided by 2, 3.75. So the speed of this person in still water is 3.75 miles per hour. And now let's find C. So again, I can use either equation to find it. So I go S plus C. I'm going to use the first one. Is 4.5. S is 3.75 plus C is 4.5. So minus 3.75. C is equal to 0.75. So let's report answers. So speed in still water, 3.75 miles per hour. Speed of the current, 0.75 miles per hour. All right. We'll take a look at more examples in future videos.